what I want to do now today is basically, the hackathon was yesterday, was a very great event, and I did this very small mini lecture, and it's very basic. Okay, so I'm glossing over a lot of the concepts actually, but it's something that I did for the participants in case there was anyone who was coming without some of the basics, in terms of like what is an EVM, what is probabilistic computing at all, like in the first place, So this is kind of like and what I will do now is I'll repeat this presentation. This is what I did at the beginning of the hackathon, although in hindsight, I later realized everyone was so much advanced. I mean, it was full of doctorate students and PhD students, and also the people in the industry who already kind of like had a lot of the knowledge. And so but nevertheless, I think it's interesting. And again, it's very simplistic. It's way more simple than what the Extropic team actually does when they like do some of the more detailed presentations. And we will not see everything. There was a video that I cannot play right now because it has some stuff that was exclusive for the hackathon participants. Mm. And that that the Extropic team will actually announce soon. So but that's fine. We'll skip that part. It's a video that is not here anyway, and I'll just get started. Okay, so cool. I mean, again, as I said, this is supposed to be a very basic a very basic introduction. So what I will do is first talk about motivation and basic concepts. Then we will see a bit of sort of build up from the ground the probabilistic algorithms in practice, in a way that we at least talk about like some of the basics, or we understand where EBMs come from, kind of, and what Gibbs sampling is. And then we will skip this video, which was a video from the Extropic team, and then basically I will go through the stuff that the hackathon teams had available for the project, for the hackathon. And if out of this video I get anyone excited to try and do a project outside of the hackathon scope, I mean, go ahead and do these. I'll be more than happy to feature that as well on the YouTube channel. And on X, I think it's all the tools and the thermal library is everything actually available, and free to use in terms of the simulators and whatnot. Um, and so I definitely encourage people to try and go and do projects. As a matter of fact, I actually had a participant that even like after the hackathon, she went back and actually did another project that was a bit, like out of the scope for the hackathon, and just she sent it as well. So it's really nice. Anyway, we'll go ahead with these. These were the sponsors of the hackathon. So obviously, Extropic was sponsoring with the technology, the content, the prices, and some of the logistics. ETH was sponsoring with the location and the management of the event itself. And then myself, as a founder of Uncertain Systems and Open Lesson, basically was kind of driving the presentations and being there to help the team as well. So the reason that I'm doing this is because, and that I did this, and that I want to do more hackathons like this, is because I think those are the very best environments to kind of like do more research around human learning, right? It fits right in the context for Uncertain Systems, for Open Lesson, and to basically connect people that want to learn stuff with companies that are building like technology and tools that are still kind of considered maybe less known and niche, but they actually have tons of potential. And obviously a university setup is the very perfect setup for this kind of things, right? And as a recap, the prize for the hackathon is basically a $3,000 prize pool, and the first winner team is going to get $1,500, the second winner $1,000, and the last one $500. The submissions will be sent to the Extropic team in the next day or two, and then we will announce prices as soon as we can. Okay, awesome. Motivation. So I think the core primitive is probably the best way to start with. And again, I know I'm probably bastardizing a lot of these, if that's the right word. So if you're an expert in the field, you probably want to kill me soon. I try to make these slides really from an amateur perspective, like sort of really like from someone approaching the field from the outside, trying to connect concepts to other things that they might have seen. So this is by far not a formal introduction to the topic, but it's done in a way that hopefully will help people connect some of the dots in terms of what is that the hardware from Extropic is built to do, and what probabilistic and thermal computing is. So in traditional computers, you have basically we're working with exact functions. So we have an input X, we want to have an output Y, and what we do, we build a program, right, as a function. So we code. This could be code, this could be like, I don't know, it doesn't really matter, right? So it's kind of an abstract way. There's a function, it takes an input, does something with the input, gives you an output. In the probabilistic realm, in the probabilistic computers side of things, we are actually talking about probability distributions. A probability distribution, and I try to make a mirror of a mirror object of this diagram. So instead of having an X, what we actually have, and we'll get into how we build this now, but what we actually have is a probability distribution. And instead of running a program, what we're doing is we're sampling, right? So essentially we are sampling, we're asking the distribution for a value, okay? This algorithm, or the way you're sampling, is kind of your program in a way, right? So there are multiple techniques to sample. Gibbs sampling is one. There's multiple ideas and multiple ways you can sample depending on the probability distribution you have. The main difference is every time that you run your sampling program, you're getting a value that will likely be different than the previous one. The reason being that these values belong to the probability distribution. This means they respect certain rules. That is what actually makes that probability distribution an object, right? But if you try to make a parallel, think of these. Think of like a classical traditional computer takes a value, has a program, gives you an output, and then in probabilistic computing, what you're doing is sampling, right? So you're creating the distribution, the probability distribution, the same way that you are manufacturing your input somehow, and you are then once you have the probability distribution, you sample it. How do we build a probability distribution? How do we build this box here? Like, how do we construct this? Very simple, naive way to do this is actually we fake it in a way, right? So that's pseudocode for a random number generator. You don't really have to understand the details of this, but essentially it's a function that we call in a classical computer, and it just has a mechanism where there is something that is hard to guess, some seed that is secret to the program. It might be something that starts off with maybe the timestamp of the chip or whatever it is. Then we're doing an operation, and out of this operation we have some boundary that we're operating with. So and essentially we return a number that is between 0 and 1, for example. I mean, you could parameterize this here. As I said, this is like something, don't pay too much attention to the correctness of the code, but the idea is we can fake a probability distribution in a way that we can fake randomness, right? So we can a random number generator is nothing else than this, something that is very difficult to predict. And you can consider a random number generator a probability distribution, right? Don't hate me for what I just said, but technically speaking, that is one way to get randomness into whatever you're building. What happens if we know some structure about the thing that we want to build, or that we want to represent with that probability distribution? Then you can build things like this. You can build sort of connected graphs, and those graphs have individual, or those nodes in this graph have individual probabilities, and so you would have the probability of something being difficult, or your intelligence. This is like the student. I think that's I had to cut the title because I couldn't squeeze it all, but it's like this is a very common textbook example where you have difficulty, intelligence, and then you kind of have the grading probabilities are a combination of these two, right? So you're building a table that is kind of a combination of these different probabilities. So what's the probability of grade 1 if intelligence is 0 and the difficulty of the exam was 0? So those are these values up here, and then essentially you build those tables. The reason this is different than this is that here we're exploiting a bit of structure. We're designing something a bit more, elaborated, right? What if we only have data? Can we build a probability distribution that basically represents this data, right? So the idea would be, I have a bunch of data and I want to build an object, a probability distribution, that when I sample it, I know that it gives me a value that is in that distribution, right? In that kind of like domain that this data represents. Yes, we can do this, and we can do this really well right now, and that kind of gets us a bit closer to why probability distribution also makes sense from a motivational perspective now that AI is sort of like so much in everyone's tongue or mouth, so to say. We can do this with, as an example, there's many ways to do this, but you can do this with neural networks, which essentially are universal function approximators. So you build your neural network that essentially approximates a function or any function, and you're approximating any function in the way that you're approximating kind of something like this, right? But it's what you end up doing later on is you build a mechanism around this to actually do conditional sampling from it, right? So you're and that's kind of essentially that kind of closes a bit what I wanted to build up with these first slides, which is probability distributions. There's multiple ways to build them, and essentially when we look at some problems nowadays, especially in the field of AI, we realize that this what we talked about in here, this structure, effectively maps to a lot of things, and one of them is actually like the essence of generative AI, right? So you're learning a high dimensional distribution, and then you're doing some kind of more advanced sampling. So you're doing like sampling. You could think of this as conditional sampling. So you have a prompt, that's the prompt to the LLM, and then you're essentially, I know what you're getting at the end of the day is just an actual answer back, but this is actually sampled from a probability distribution of potential answers, right, inside the box. That is why Extropic is putting so much emphasis on the potential applications of their chips for AI, right? There's many other applications for probabilistic computing or computer and chips, but this is one because essentially all this sampling, everything that we're doing here is very GPU intensive, right? So currently we are using classical circuitry to build these, to do the sampling, to do the whole process, right? And this means we're using GPUs because they're good at the math behind these models, but at the same time, they're expensive to run, and they in terms of energy, right? And compute also, but like in terms of energy, they burn a lot of energy. So now that we've talked a bit about these, right? So we, again, to sum it up a bit, is like we talked about like the difference between the traditional computer and what a probabilistic computer is in its core primitive, right? Now, how does a probabilistic algorithm look like, right? Because we know our classical algorithms well, right? You have like tons of different things you can design in a computer as an algorithm, but how does a probabilistic algorithm look like? What I will do is I will build this up for using an example that is very simple. It's not the best example to explain this, but it's an example that is easy to go from a very stupid approach to this problem that is purely deterministic and bad quality, to a probabilistic one, to something that helps us understand why EBMs make sense and why like energy-based models, where do they come from, right? So the example is we've got basically a noisy observation, and we're trying to kind of clean it up. We're trying to clean up these and basically get like a clean image, which is like the letter E, right? And let's maybe, I know this happened in the hackathon as well. I know some of you are like into machine learning, into some of these like more advanced algorithms, and you go straight into like a setup where you will like do some training on something, and whatever, you would apply some algorithms. I'm the first step for me is way more stupid, right? It's way more simple. It's to say, what is the dumbest way you can implement these, right? The dumbest way you can implement these, and I probably have to put my face a little smaller here. I'll do that so that you can see more of the slides. The dumbest way that you can do these is by applying that box diagram we saw at the beginning. Something classical, very simple. A very simple thing. We go pixel by pixel, the pixel here in the middle. We go pixel by pixel, and we just look at the neighbors, at the pixels surrounding it, and then we say, whatever the biggest amount of is, then, if there's more whites, then we're going to turn these into white. If there's more blacks, we're going to turn this into blacks. Very naive. And we will get something out of these, right? But it's going to be rather like, it's going to actually have bad quality, right? Because it's not really going to clean up well. Like if we end up with an image where, there is tons of tons of noise here on a corner, it's not going to process this well. But I mean, you can try to approach it like this, right? So the problem is you always get the same solution, right? So, when you think about like, okay, could I implement that differently? Could I implement that with some randomness to it? Could I implement that with a probabilistic algorithm? Nothing to do with machine learning, nothing to do with AI, right? So we're still in the realm of like, how can I use probabilistic algorithms to implement better solutions to things like this? You could do, and obviously you would do that per pixel. You would then kind of like swipe pixel by pixel, right? You would move the window. So let's add some probability to the mix. So now if we want to approach it like these, we need to add some sampling step, right? So one way to approach this would be to basically have a similar approach, but instead of just counting and doing a classical if, we would count the proportion of white, the proportion of black, and we will transform that into a probability, right? So we would say, perfect. So if there is a certain percentage of white, that's going to be the probability of it being white versus the probability of it being black. It works nicely because we have essentially, they would both add up to 1, right? Because we know that whites plus blacks must be 8, so 8 divided by 8 is 1. That's an important property of a probability of to have like a normalized probability distribution, that it always must add up to 1. And then we would implement the probability aspect of that solution, which would be basically, hey, if you pick a random number generator, like you pick a random number between 0 and 1, that's actually the randomness, or the sampling in this case is happening at that level. You pick a random number, and if this number is smaller than the probability of black, then the PB, probability of black, then we turn that into black, if not into white, right? What will these do? What will these do to the solutions? It will actually, if we run this algorithm multiple times, then we do the same. We swipe the pixels, right? But let's just imagine you do this one time, you get one solution. You're going to run it another time, you're going to get another solution, right? So then you can basically do these multiple passes, multiple swipes, and at the end of everything, either pick the best solution or pick an average solution. It will essentially help us get out of that static local minima, if we want to call it like this, that the deterministic algorithm was giving us, right? But we can definitely do better, right? We can do better than this, because, as I said, if there's ways to structure things, right? Remember this slide here, right? So if we know some structure, we can actually be a bit smarter about how we design this, right? So let's try to add, pause this for a second if you're watching it later, because I know I'm live streaming it right now, but later on I'm going to put this on YouTube. If you can pause the video now if you're watching this on YouTube, and try to think about what structure do we know here that would help us do this in a smarter way. So obviously a piece of structure we've already revealed, right? We are implicitly saying here that we care about what the neighbors are telling us. That somehow we're implicitly, by designing it like this, we're implicitly saying that the pixel here somehow somewhat depends on those. That's a bit of structure already. But there's something that you could add here that is missing, that is essentially the pixel itself carries more information, right? We know it's a noisy observation, but that doesn't mean that these pixels are always wrong. Doesn't mean we have to correct them, right? So there is a degree of trust that we could parameterize, that we could put in here that says, look, I'm sure, because of whatever the factors I know, I'm sure that the quality of the pixels is 80%, right? So 80%, I should keep the color, right? Not always, like, but that you kind of have that extra parameter there that tells how much confident you are that this is actually black, right? And that it doesn't really need to be corrected. It's kind of a second layer. It's a bit of structure, right? So essentially, that is something that then you end up being able to build some kind of structure, right? You say, cool, so I will maybe do something like these, and then connect it with the probability of how much I think these guys should influence, right? So at this point, what I want to introduce is the fact that, and this is maybe the biggest leap in the presentation, right? So I'm definitely skipping a lot of things here, not going too much into detail, but for the purpose of getting to where energy models come from, there is a way you can basically generalize what I just said, right? You can build this function, a function that expresses these constraints that I just said, and then this function is something that you can then optimize, right? And try to basically do multiple passes and parameterize this function so that you minimize it. And you should be, if you're not familiar with minimization problems or optimization problems in computer in programming, or even in just the most pure mathematical sense, go ask Grok or some LLM, the LLM of your choice, and they'll help you there, right? But the idea is that you can use this to optimize. So you can parameterize once you have a problem expressed as a function, right? Once you have a problem expressed as a function, if you're smart enough, to express this function in a way that the minimal values of this function are actual solutions you're looking for, then you're getting something that you can optimize mathematically, right? And then find an optimal solution. This is where physics kind of gets involved into this picture, right? And then we have basically Mr. Boltzmann or Maxwell Boltzmann. I'm sorry if I'm quoting the wrong names. I know that essentially the concept here is, for those who are not familiar with these, in physics there is a very similar concept that is very grounded to actual physics, right? Which is basically a probability distribution that relates how is the energy of a system how is the energy of the particles of a system spread across the system at a given temperature, right? And if you go and check these out, you will notice that these probability distributions have these very nice curves that almost look like a normal probability distribution, right? Which a normal probability distribution is very nice because it's clean in the sense that it only assumes one thing about the data. It only explains one thing about the data, which is basically how concentrated you are in your average value, right? And so this is something that then physics came in and said, look, it's great because we have actually a way that physics already kind of has a way to create these functions, these energy functions. These energy functions actually have they can be parameterized. Temperature can be a parameter, and this is something that lets us then play with, play with how concentrated or spread the probability distribution is. Which, if we think about optimizing algorithms, it's a great mechanism to do exploration versus exploitation. And it makes, as I said, the minimal assumptions. It's also, and I know here I'm making a big leap, right? So go and take a screenshot, go ask Grok if you want to deep dive into this. But essentially it's compositional. So this means that if you have a system and if the system is split into small parts, the sum of these energy functions of the small parts kind of equals the sum of the entire system, which mathematically it's very convenient for working with probabilities. And so people say, well, look, we can actually use these, right? We can take the same concept. We can take this problem, formalize what I just said about like the energy relation, not the energy, sorry, about the constraints and the different, probabilities of like how much we trust these and how much these guys should influence. We can formulate that as an energy function, and then use the physics principles behind these to turn these into a probability distribution, right? Why is this good as well? It's good because it's something that is closer to the physical world. This means that the chances that we can implement something in the physical world that help us do these calculations natively without using software per se, then then it's actually, it gives us kind of a pathway to being able to solve these problems more efficiently. This is where that's the reason why these things are called EBMs, energy-based models. So why model? Because you're modeling something, you're modeling your problem, and it's energy-based because essentially it's using this framework, which is basically the energy framework for as a probability distribution, right? Or as a basis to make a probability distribution. This is where you get the scary formula. So, and I think what I put in here is the sample window of pixels that we had. And I'm going to move my face a little more so you can see the formula. But essentially that's, we can break this down easily to show this, right? To show you the parameters. So it's the energy of this local window here that we're looking at, right? Because we said, look, we don't need to look at all the pixels. We can just look at this one and then at the neighbors. So that's why I said compositional makes sense, because then you can add up everything and it adds up to the energy of the total system. And so you're saying here, and you can take a look at the legend calmly if you want to pause the video. The way that you build this formula to represent the constraints that I talked about is basically saying, look, we're going to define the energy as basically two main components that you're adding, right? So look at these plus here, just focus on the first component, and then we focus on the second component. The first component has V minus Y sub I. So V is the candidate value, right? Let's say we're focusing on calculating the energy for the value 0, the pixel being white, right? And then we're actually, calculating these with like kind of in relation to the noisy observation of that pixel, which is black, right? And then we're adding the weight of the data term. That's basically how much we trust the noisy input. That's what I talked about, like how much you want to be confident on the value of that pixel, right? So that's one component of this structure. These plus, then basically this is a component of this formula that it's adding. Basically, this looks scary if you are not into mathematic formulas, but it's nothing else than a sum of all the vertices around it, and you can take all of them, maybe just 4 of them, I don't know, it doesn't matter. Take all of them here, and you're essentially doing the same concept. You're just comparing them with the expected value, or the value that you're calculating the energy for, and you're multiplying these by another weight, which is basically how much it represents, how much the neighbors should agree with the color of the pixel at the center. I don't want to spend too much time on these, but you can again go look it up, do a bit of a deep dive. But essentially, that formula is encapsulating the structure. Here structure was, I put it in a very nice graph way, but you can also have structure with a formula, right? So that's the structure that we're putting in here. And what's cool about this is that then you have a very easy way to transform this energy into a probability distribution, essentially turning the low values, and this is then just based on the physics transformation that is done to go from energy to the probability distribution, which is basically adding the exponential of the negative energy, and that makes that transformation. That's exactly what we want, because we want a probability distribution that is high probability when the energy was low, because we designed these formulas so that if this value is 0, then it means we have the solution we want, right? And then essentially what you do is you just do this. You compute the energy of the states you want, you convert it into a probability, you generate a random number, and then you do the same thing, you do the sampling, right? Now, this is okay. So we talked. We kind of went from a very naive, stupid idea into modeling a problem with an EVM. Okay, that is just one very specific example. But the idea here is this concept of this formula is something that you can then apply to whatever problem you want. You have your problem, and you can try to map it into this. You can try to build an energy function. And there's a lot of things you can do in here. Then also with the thermal library from Extropic, because there's subtypes of energy functions or EVMs actually. You can build EVMs that are more like a node of graphs, like in this case where you have things connected, but you can also just build more generic EVMs as well, right? With different energy functions. So EVM, the EVM concept, hopefully it's clear. That's where EVMs come from. And remember the word EVM because EVM is actually one of the primitives or one of the working blocks, not primitive, one of the working blocks of the thermal library. Why do we need specialized hardware at all to do these things? Well, we looked at an example of the image, and as I said, you still need to do the sampling, you still need to do a lot of iterations. You basically train those EVMs, those parameters, to give you good answers, but like you need to do a lot of swipes, and that involves sweeps, and that involves a lot of iterations. With computing the local energies, generating the random numbers, there's a lot of software iteration that is very energy intensive. It's tractable up to a certain number, but it also quickly becomes intractable. And so probabilistic hardware essentially is performing these operations natively. Instead of just doing the calculations or having the mathematical operations of adding and multiplying and whatnot, it's the primitives of the software, of the hardware, are actually running those things natively using physical phenomena on the chip. This essentially reduces the need for all the millions of software iterations that you kind of need to do otherwise, right? So what's inside the chips of Extropic? This is something that you can also go and take a look at their website. Actually, I highly encourage you to do that. You can actually go to extropic.ai. They have a great writing section where they explain a lot, and then there's a few things in here. Wait a second. There's a few things. Let's see if I can find this. The intro, computer from zero. I think it's this one. Yeah. Here you have some very nice also interactive animations that you can play with, and you can see how. I have it linked later. I have it linked later. The exact one that I want in the slides. So I'll talk about this in a second. But essentially, these are the what's inside these chips, right? So you have probability bits, p bits, probabilistic bits, p bits, which are essentially components that are not just something you can read as a 0 always or a 1, but they keep oscillating between 0 and 1, and you can actually control how much time they spend on the 1 state, how much time they spend on the 0 state. So you can create, probability distributions with these pieces. Then they also have PDITs. So if you want to go categorical, this means if instead of 0 and 1, you want to have 0, 1, 2, and 3. So 4 states, that's one example. And then you have more advanced P modes and PMOCs. But essentially, those are the primitives I was talking about, right? You don't have to break your problem down into like the basic assembly operations that we all know computers run with, and then the basic transistor type bits, but you actually have these probabilistic native probabilistic units inside the chip, right? So essentially what the hardware does is it does the sampling natively. That there's an animation of these on the website as well. So I'm gonna skip that. Now we're not gonna have the video because we don't have it here, and there's a bunch of stuff in there that I cannot share. Before that was basically the main part of the lesson, of the mini lecture, to get you started with what an EVM is really at all, and then we went directly through tools for coding. So essentially what we have here is Extropic released a coding agent skill, which is actually very, very cool, that is available here. I can go visit these links now. So we have this coding skill here that I actually recommend a lot, because it's amazing to then get to work with thermal very quickly. So you don't need to kind of know all the details of the thermal library. And then we had we have basically the new thermal documentation that they've actually revamped and released, with a lot of examples and stuff like that. So this, definitely recommend going through these. Um, you have examples, there's tutorials, getting started with these, and these are the docs, but essentially the actual library is here available. It's open and available for free, so you can actually use it. And what's cool about this library is that it comes with a simulator as well, so you don't need to have actually access to the hardware from Extropic to run these algorithms. You can run them on GPUs, right? So if you have access to a GPU, and 4090 should probably be enough, but if you and that's what we did here for the hackathon. If you didn't have access to one, so we gave you an API key for Prime Intellect. That's not valid anymore. You can screenshot that if you want. It's invalidated, so you're not going to drain any credits from there anymore. But essentially, those were the tools that the teams had ready to use for the hackathon. And then we gave the hackathon participants a few ideas on what could they do from a creative side and also more scientific side. So we talked about and again, those were just ideas to kind of like break the ice a bit, right? Because it's the whole purpose of this hackathon as well, and the whole purpose of these is like the probabilistic computing community needs more influx of people interested in the topic, and finding applications for these is not that easy, right? Because it's hard stuff to understand if you come from outside that industry. And that's why I thought we'll put a few slides here where we'll look at like procedural terrain generation, for example, some music stuff. And actually one of the teams ended up doing like a music project, generative art as well. So essentially everything is how to reduce certain problems to like specific EVM types, because if you go and look at the documentation, that's the whole point here, right? So the application, like the library supports or gives you tools to basically create energy-based models. Discrete EVMs, Ising models are like, they have some like pre-trained models, and essentially you can use these models to then and then do sampling on them, right, efficiently. And so basically we talked a bit about as well some scientific ideas, like some protein folding. One team actually did protein folding as well as part of the project in 2 dimensions. Material simulation, multi-agent pathfinding. Another team did multi-agent pathfinding actually as well. Very cool results. And basically that's it, really. This was the introduction. We spent some time, took me I think 38 minutes, 40 minutes to do that. And then the teams went off to code. And as I said, if you're willing to do a project on your own and you want to send it over later for me to feature it on the YouTube channel, I will do that. I'll be super happy to do that. And what I will be doing in the next days and weeks is I will actually do a very deep dive on each of the projects. If the team gives me the permission, I will do a deep dive on each of the projects. We'll go through their slides, their presentations, their code. We will actually try the projects. And obviously, in the meantime, the Extropic team is going to be reviewing the submissions, and then we'll pick a winner. Cool. I hope this was useful. I hope you liked the presentation. As I said, apologies from the deepest parts of my heart if you're an expert in these and you probably spotted like 10,000 mistakes in the way that I explain things. I am trying to explain these in a way that it's kind of as accessible as possible to someone who has no idea about like any of these. And I myself, I'm not an expert, but I'm continuously learning about this kind of stuff. If you want to go through these and then you want to test your knowledge as well, remember that here in the original post of the hackathon, we actually posted as well a link to Open Lesson, Write the Noise. It's a workspace that we prepared where you can actually go and talk to a Socratic tutor and then basically sort of get a feel of like where your knowledge gaps are in this topic. Okay, cool. So wait a second. I did have a link to these. Give me a second. I did have a link to these that I want to share. Here, before I forget, this is the link, and this was the other link as well. I'll probably share the slides. No, that's the link, because this is a very interesting article where they actually explain how TCOs work, so you can have like some interactive, if you want to play with some of these visualizations, help you understand some of this stuff. And then you can here, see the energy functions and the probability distributions. You can see how two different probability bits can interact with each other, how like a more complex setup, and you can basically play with the temperature here. Yeah, so I definitely recommend giving a read at these. And yeah, I hope that was useful. See you guys tomorrow.